In the first part of this lecture, we set up a material balance inside a catalytic pellet in order to understand the effect of reaction and internal diffusion on the reactant concentration and overall rate of reaction inside the catalyst pellet. The material balance resulted in a second order differential equation for the concentration of reactant A as a function of radial position in the pellet. We transformed this differential equation in terms of dimensionless quantities, the dimensionless concentration psi and dimensionless radial coordinate lambda. From this, we defined the Thiele modulus, which is a very useful parameter because you can use it to infer something about the relative strength of reaction and diffusion inside the catalyst pellet without solving the differential equation. So this is our second order differential equation in terms of the dimensionless quantities and the two boundary conditions needed to solve the differential equation, also in terms of the dimensionless quantities. Now, to find out more what is going on inside the catalyst particle, we need to solve the differential equation with the boundary conditions. To help solve it, we now introduce a variable transformation. Y is equal to psi times lambda. Why this transformation? Well, lots of mathematicians tried to solve this problem in the past, and they tried lots of different transformations until someone found the transformation that makes the equation reduced to a simple form, something that has a recognizable solution. Often, it is just trial and error until you find something that works. If you need to solve a differential equation via a transformation in the exam, then I will give you the transformation to use. This is the differential equation that we need to solve. And we have two boundary conditions. Boundary condition 1, so at the surface of the pellet, so that's at lambda equal to 1, the dimensionless concentration psi is equal to 1. And boundary condition 2, at the center of the pellet, so that's at lambda equal to 0, the dimensionless concentration psi is finite. Our aim is to find a solution which is psi as a function of lambda, from which we can solve the concentration profile. So Ca as a function of the radial coordinates r. So to solve this, we need to transform it into a simpler form, and we can use this transformation to do that. So y equal to psi times lambda. So we would like to express this equation in terms of y and lambda. So here the dependent variable is psi. when we transform it, we would like the dependent variable to be y, and the independent variable is still lambda. So we need to find an expression to replace the second derivative of psi with respect to lambda with something like the second derivative of y with respect to lambda. And the same thing for the first derivative. Okay, so from this, y is equal to psi times lambda. Okay, so we can express psi as y divided by lambda. So we can then take the first derivative of psi. So first derivative of psi with respect to lambda is, okay, so we can use the product rule. Okay, so we'll have, so first let's differentiate y. So we'll have 1 over lambda dy d lambda plus, okay, so this time y will be constant and we will have to differentiate 1 over lambda. So we have y, and the derivative of 1 over lambda is negative 1 over lambda squared. Okay, so the first derivative of psi with respect to lambda is 1 over lambda dy d lambda minus y all over lambda square. So if we differentiate this with respect to lambda, then we will get the second derivative of psi with respect to lambda. Okay, so we need to differentiate this expression. So we will have to apply the product rule twice. Once for this term and another one for this term. Okay, so let's do that. So let's do this one first. So applying product rule. So first, let's hold 1 over lambda constant and differentiate with respect to dy d lambda. So we'll have the second derivative of y with respect to d lambda. Plus, so this time we will hold dy d lambda as constant. And we will have to take the derivative of 1 over lambda, which is equal to negative 1 over lambda squared. So now let's apply the product rule to this term. So we'll have minus. Okay, so first, let us hold 1 over lambda squared constant and differentiate y. So we'll have dy d lambda. And then, okay, so plus. So this time we'll hold y as constant and differentiate 1 over lambda squared. So the derivative of 1 over lambda squared is negative 2 over lambda cubed. Okay, and then we can simplify. So this is equal to 1 over lambda d squared y d lambda squared minus 1 over lambda squared dy d lambda minus, okay, so I'll have 1 over lambda squared dy d lambda. And then this one, so I have 2 minus signs, so that will become positive. And then I have 2y over lambda cubed. Okay, so my second derivative of psi with respect to lambda is equal to 1 over lambda, second derivative of y with respect to lambda. So I can combine the two terms here. So we'll have minus 2 over lambda squared dy d lambda plus 2y over lambda cubed. Okay, so now we have an expression for the first derivative of psi with respect to lambda, and the second derivative of psi with respect to lambda in terms of y and lambda. Okay, so we can substitute these expressions into our differential equation. Okay, so let's do that. So first we have the second derivative of psi with respect to lambda, which is just this expression. So we have 1 over lambda d squared y d lambda squared minus 2 over lambda squared dy d lambda plus 2y lambda cubed. Okay, and then we have plus 2 over lambda times the first derivative of psi with respect to lambda, which is this expression. Okay, so we have 1 over lambda dy d lambda minus y over lambda squared. And then we have minus phi squared times psi raised to n. Okay, but psi in terms of y is y over lambda. So this term here, I can write that as y over lambda raised to n equal to 0. Okay, so let's evaluate some expressions and try to simplify this. So we'll have 1 over lambda is the second derivative of y with respect to lambda minus 2 lambda squared dy d lambda plus 2y over lambda cube. Okay, so let's evaluate this. So we'll have plus 2 lambda squared dy d lambda minus 2y lambda cube minus phi squared. So this one I can write as y raised to n divided by lambda raised to n equal to 0. Okay, so you can see that some of the terms will cancel out. So this term here, which has a minus sign, will cancel out with this. Okay, and this term here will cancel out with this one. Okay, so our expression is now 1 over lambda, second derivative of y with respect to lambda, minus phi squared times y raised to the n divided by lambda raised to n equal to 0. And then I can multiply both sides by lambda. So I will have d squared y over d lambda squared minus phi squared y to the n. Okay, so I'll have lambda raised to n minus 1. Okay, so because I have lambda raised to n and I have 1 lambda here. Okay, so this is equal to 0. Okay, so if we have a reaction with order n equal to 1, okay, so the phi, so without a subscript n, is understood to be of order n. So this is the same as saying phi to the n. This is nth order, but for first order reaction, n equal to 1. So we have to write phi subscript 1. Okay, so let's write this for order 1. So we'll have squared y d lambda squared minus, so we'll have phi 1 squared, and this is y. So the denominator lambda n minus 1, so this will become 1 because n minus 1 is 0 and that is an exponent, so the denominator will be 1. Okay, so we have simplified our differential equation to this one by transforming it using this transformation. We have transformed our differential equation into this, which is for a first order reaction. This is a very easy equation to solve. We saw the solution to this in the maths revision sheet, and it was one of the questions in the Kahoot quiz. We know that both cosh phi 1 lambda and sinh phi 1 lambda are solutions. So the most general solution is a linear combination of this. Now that we have the solution for y, we can go back to the original dimensionless concentration psi, and we can apply the boundary conditions to obtain the values for the constants a1 and b1. We can evaluate a1 using boundary condition 2, which requires that psi remains finite at lambda equal to 0. At lambda equal to 0, cosh of phi 1 lambda is equal to 1, and sinh of phi 1 lambda is equal to 0. So our solution at lambda equal to 0 is a1 over lambda. So if a1 is finite, then psi is infinite, which contradicts our boundary condition. That means that a1 must be 0. To put it another way, we had two possible solutions to our equation: cosh phi 1 lambda and sinh phi 1 lambda. But cosh phi 1 lambda goes to infinity at lambda equal to 0. So it is not a physical solution. We can only use the other solutions, sinh of phi 1 lambda, which is the physical one. So now our solution is just psi equal to b1 sinh of phi 1 lambda divided by lambda. We can obtain the value of b1 from the other boundary condition, bc1, which says that psi equal to 1 when lambda is equal to 1. Putting that into our solution gives us that psi is equal to 1 equal to b1 sinh of phi 1, which means that b1 is equal to 1 over sinh of phi 1. Let's do it on paper so I can show you step by step. So our differential equation is this. Okay, so we know the solution to this. We know that this is a solution. Y is equal to a1 cosh. Okay, so we have phi 1 lambda. And this is also a solution. Okay? So meaning if you substitute each of these expressions into the differential equation, then it will satisfy this. Okay? So a more general solution is a linear combination of the two. So we can write y equal to a1 cos phi 1 lambda plus b1 sinh phi 1 lambda. Okay, so let's write y in terms of our dimensionless concentration. So we use this transformation. So y is equal to psi lambda. So in terms of our dimensionless concentration psi, our solution is a1 over lambda cos psi 1 lambda plus b1 over lambda sinh phi 1 lambda. Okay, so now we have to determine the constants a1 and b1 using our boundary conditions. So let's use our second boundary condition first. So BC2 states that at the center of the pellet, so that's at lambda equal to 0, it requires that psi is finite. Okay, so we will have to evaluate this at lambda equal to 0. Okay, so we will have to recall our hyperbolic identities. So we have, okay, so cos x, this is equal to e to the x plus e to the minus x over 2. And sinh x is equal to e to the x minus e to the negative x over 2. Okay, so psi is finite at lambda equal to 0. So we have a1, so lambda is 0, cos of 0. So using this, cos of 0 is 1. This is 1. Okay, and we have b1 over 0. Sinh of 0 is 0. Okay, so the only way for this to be finite is when a1 is equal to 0. Okay? Otherwise, it will become infinite. Okay? So remember that a number divided by 0. Okay? So for example, 1 over 0, that's infinity. Okay? Whereas 0 over 0 is not necessarily infinite. Okay? So it is indeterminate. Okay? And we don't want this to be infinite. So the only way for that to happen is when a1 is equal to 0. Okay? So another way to look at it is we can throw this term away because this is not physical. Okay? It makes our solution goes to infinity when lambda is equal to 0. Okay? So therefore, a1 is equal to 0. So our solution now is psi is equal to b1 over lambda sinh phi 1 lambda. And we can determine b1 from boundary condition 1, which states that at the surface of the pellet, so that's at lambda equal to 1, psi is equal to 1. Okay, so we can just substitute the boundary condition into this. So we have 1 is equal to B1 divided by 1. Okay, sinh phi 1 times 1. So I'll just write sinh of phi 1. So therefore, B1 is equal to 1 over sinh of phi 1. So therefore, our solution psi is equal to sinh phi 1 lambda over lambda sinh phi 1. Okay? So we know that psi, this is equal to CA over CAS. And this is equal to sinh phi 1 lambda over lambda sinh phi 1. So this is our solution. So let's go back here, because some of you may be wondering why when lambda is 0, the sinh term is okay. So we have this term. Okay, so at lambda equal to 0, we can't really calculate this because it will only give us 0 over 0. So the only way to calculate this is to take the limit as lambda tends to 0. Okay, and if you remember your L'Hopital's rule, which says that the limit as x tends to 0 of fx divided by g of x, this is equal to the limit as x tends to 0 of f prime of x divided by g prime of x. Okay, so let's apply L'Hopital's rule to this term. So taking the derivative of the numerator divided by the derivative of the denominator, so we'll have b1 phi 1 cos phi 1 lambda, okay, divided by the derivative of the denominator, which is 1, and then we'll take the limit as lambda tends to 0. Okay, so we'll have cos of 0, which is just 1. So this is equal to b1 phi 1, which is not infinity. This is the expression that we derived, which gives the concentration of A at every point R in the catalyst pellet. Note that lambda is small r divided by big R. Therefore, we can calculate the rate of reaction of A at every point, and this is what we need to work out the overall rate of reaction, or how much A is consumed over the whole catalyst particle. If we plot this function against lambda for various values of the Thiele modulus phi 1, you can see its effect on the concentration profile. For low values of phi 1, so say 0.01, the concentration is nearly equal to its surface value throughout the pellet. This is the effect of the diffusion being much faster than the reaction. The reactant can penetrate all the way into the pellet before it is consumed by the reaction. At very high value of the Thiele modulus, so say phi 1 equal to 10, the reaction rate is much faster than diffusion. So you can see that the concentration drops to nearly 0 halfway into the pellet because the reaction consumes all of the reactant before it can reach the inner parts of the pellet. At an intermediate value of phi 1, we get a bit of both situations. The reaction and diffusion occur at about the same rate. So the concentration drops within the pellet, but all parts of the pellet have a reasonably high reactant concentration. Having obtained a concentration profile in the pellet, we can calculate what we really want to know. What is the overall reaction rate? We can get this by integrating the rate of reaction over the whole catalyst volume. The result for a first-order reaction is as follows. It is a function of the surface reaction rate and the Thiele modulus only. It is useful to be able to express this overall rate as a fraction of the maximum possible rate when there is no diffusion resistance at all. So the parameter eta, which is called the effectiveness factor, is defined as the actual observed rate divided by the rate that would occur if there were no diffusion resistance. For our first order reaction, the effectiveness factor eta has a simple form. So how did we derive the expression for the effectiveness factor eta? So let's do this for a first order reaction n equal to 1. We can derive this from the expression for the concentration profile that we derived earlier. So we found that psi, or the dimensionless concentration, this is equal to Ca over Cas. This is equal to 1 over lambda sinh of phi 1 lambda divided by sinh phi 1, where lambda is equal to r over r. Okay, so using our concentration profile, we can write an expression for the rate, for the reaction rate at every point in R. Okay, and then from there, we can write the expression for the total rates for the whole pellet, and then use the definition of the effectiveness factor. Okay, so what is the definition of the effectiveness factor? So we define this to be the ratio between the actual observed rate and the maximum reaction rates. Okay, and the maximum rate occurs when you don't have resistance due to internal diffusion. Okay, so effectiveness factor is actual observed rate divided by the rate in the absence of the internal diffusion resistance. Okay, so if you don't have any resistance due to internal diffusion, it's as if the entire interior, or all points inside your catalyst pellet, were exposed to external concentration. Okay, so at all points inside your catalyst, the concentration is the same as the surface concentration because you don't have resistance due to internal diffusion. So this is the rate at CAS. Okay, so we will write that out later. But for now, let us write down the expression for the actual observed rate. So how do we derive this from the concentration profile? Okay, so we have the different definitions for the reaction rate. And for this one, it is most convenient to use the per volume basis because we can multiply that by the volume of the control volume to get the total rates. So let's do that. Let's write the volumetric reaction rate. So that's negative RA. So without any primes. And this is a function of the radial coordinate r. So this is per volume basis. So if we assume first order reaction, this is equal to the rate constant times the concentration of A. And the concentration of A is a function of the radial coordinate r. Okay, so from topic 2, we know that the units of this is mole per second per unit area. So this is the per surface area basis. Okay, so this is per m squared. But I would like the unit of my rate to be mole per second per m cube. Okay, so if we multiply this by the specific surface area, the units of this is m squared per kilogram. So this whole term will have the units of per kilogram catalyst. Okay, but we want per volume, so we have to multiply this by the density of the catalyst. Okay, so now we have the right units, mole per second per m cube. Okay, so from this, we can derive the total reaction rate. Okay, so this is the rate at every point inside the catalyst, at every point R. So if we multiply this by the volume, so this is per volume, multiply by the volume of the control volume, and then if we integrate over all R, that would give us the overall rates or the total rate. So the total rate, RA total, this is equal to the rate at every point R. So this is per volume. So let's multiply this by the volume of the control volume. So that's the surface area of the control volume times the thickness of the control volume. So surface area of a sphere, okay, surface area of the control volume for a spherical shell is 4 pi r squared. So the volume is the surface area of the control volume times the thickness of the control volume, so times dr. And then we have to integrate this over all r. So from 0 up to the radius of our catalyst pellet, capital R. Okay, so now we can substitute the expression that we have for RA of R and then evaluate the integral to get the total rate. So let's do that. So we'll have RA total. This is equal to the integral from 0 to R. So now let's use the expression that we have for RA of R. So we have rho C, SA, K, CA of R, and then we have 4 pi r squared dr. Okay, so let's take the constants out of the integral. So we'll have 4 pi rho C, SA, and K. Inside the integral, we have CA of R, r squared dr. Okay, but we know our concentration profile. So this is the expression for Ca as a function of r. Okay, so let's substitute that into here. Okay, so this is equal to, so 4 pi rho c as a k. Okay, so now we will use the expression for the concentration profile to replace this Ca here. Okay, so I have Ca over Cas, so I will have Cas here on this side. So we'll have Cas. Okay, and then Ca. So Ca is equal to Cas over lambda. Okay, times sinh phi 1 lambda over sinh phi 1. Okay, so that's our Ca. And then we have r squared here and dr. Okay, so this is equal to, so again, we can take out the constants. And then let's define the lambda in terms of the radial coordinate, r. Okay, so we'll have 4 pi rho c s a k. So we have Cas outside. And then 0 to r. Okay, so lambda is equal to r over r. So we have 1 over lambda here. So we can write that as capital R over r. Okay, so this is 1 over lambda. And then just write down the rest of the expression. Okay, so now I can take out the capital R of the integral, and I have 1 r here in the denominator and 2 r's there. So I can simplify this. So we'll have 4 pi. Okay, so this r is from this one. So we have rho c s a k cas 0 to r. So now we have, okay, sinh phi 1 is also constant, so we can take that out of the integral. So sinh phi 1. So the terms left inside the integral are, so we have r, okay, so r squared divided by r, and then we have sinh phi 1 lambda, okay, dr. Okay, so I forgot to define this in terms of r, so let's do that in the next step. So 4 pi r rho c s a k cas sinh phi 1, so 0 to r, okay, so r sinh phi 1, lambda is r over r dr. Do you still remember how to solve this integral? So we have integral from 0 to r of r sinh phi 1 r over r dr. So what's the integral of this? How do you evaluate this? Okay, so we will need to use integration by parts. In the maths revision sheet that I provided you, there is a formula for integration by parts. So let's write that down here. So we have the integral from a to v of the product of two functions that are function of x. Okay, so u of x, and v of x. Okay, so we have u times v dx. And this integral is equal to, okay, so we have u and the integral of b dx and this needs to be evaluated from a to b, minus, so here the next term will have a double integral. So we have integral from a to b, and then the inner integral, so we have v dx, okay, times du dx, and then we have an outer integral. Okay, so this is the formula from the maths revision sheet. I hope you remember how to integrate by parts. Okay, so this is the expression that we need to integrate. So we can divide this into two functions, r and sinh. So we can see here from the formula for integration by parts that we have du over dx. So we normally want our u to be the simpler function. Okay, so the one with the derivative here, we want that to be the simpler function. So in our problem here, that means that we can define u as r, and then v is the other function, which is sinh of phi 1 r over r. Okay, so now we just need to apply the formula for integration by parts. Okay, so I'll put the argument of the sinh function inside the bracket, so it is not confusing. Okay, so let's apply this. So integration by parts. So this integral here, okay, so that's equal to, okay, so the first term, so u, our u is r, times the integral v dx. Okay, so v is sinh phi 1 r over r. So dx, in our case, that's dr. Okay, and then we have to evaluate this whole thing from 0 to r. Okay, so next term, minus, so we have the outside integral, so from 0 to r. Then we have the inner integral, so that's v dx. So in our case, that's sinh phi 1 r over r dr. Okay, and then we have du dx. Okay, but du dx is just dr, so just times 1. Okay, and then the integral of that. Okay, once we have evaluated the integral, we have to take another integral. Okay, so for the outer integral, dr. Okay, it's the whole expression here, dr. Okay, so let's evaluate this. So this first. So we'll have r. Okay, so although it looks daunting, it is quite simple because of the property of the hyperbolic functions. Okay, so if you can remember the derivative and integral of hyperbolic functions. Okay, so the integral of sinh is just cosh, and vice versa. Okay, so let's take the integral of this. So sinh phi 1 r over r. So the integral of that is just cosh. So we have phi 1 r over r. Okay, so since we have constants inside the argument, so we have to divide this by the constants. Okay, phi 1 r. Okay, and we have to evaluate this from 0 to r. Okay, so what about this one? So 0 to r. So let's evaluate the inner integral first. So the inner integral, so we have cosh phi 1 r over r divided by phi 1 over r dr. Okay, so let's evaluate it further. So this one we can now evaluate at the limits of integration. So let's first do it for capital R. So we'll have r cosh Okay, so I'll have phi 1, and then this r here will become capital R's, and we'll cancel out with this one here. So I'll just have phi 1 here, okay, divided by phi 1 over r minus, okay, so the lower limits of integration, so 0. So r, so this is 0, okay, so that is only 0. Okay, minus, so now let's deal with the second integral here. Okay, so just evaluate the integral of cosh. So the integral of cosh is just sinh phi 1r over r. Okay, and then we have to divide by the constants in the argument. So we'll have phi 1 squared over r squared. Okay, and we have to evaluate this from 0 to r. Okay, so evaluating that, so this is our first term. Minus, okay, so let's evaluate at the limits of integration. So first is at the surface of the catalyst, so minus sinh, okay, so phi 1, and then here you'll have capital R over capital R, so they will cancel out. So I'll only have sinh phi 1 here, and then the denominator phi 1 squared r squared. And then at the lower limits of integration, so sinh 0 is 0. So we can have minus 0. Okay, so this one should have a bracket here. Okay, so therefore our expression, so this integral here is equal to, okay, so r squared phi 1 cosh phi 1 minus r squared phi 1 squared sinh phi 1. Okay, and then I can factor out r squared sinh phi 1 over phi 1. Okay, so my first term will become, okay, so factor this out, and I will have cosh phi 1 over sinh 1. So I'll have 1 over tang phi 1. Okay, so minus, so for this one, I'll only have 1 over phi 1. Okay, so this is the integral of this. Okay, so now we know this integral, so we can write the expression for RA total. Okay, so RA total is just this bunch of constants times the integral. So let's write that down. So we'll have RA total is equal to, okay, so we have 4 pi r rho C S A K CAS over sinh 1 or sinh phi 1, okay, times the integral, which is this. So we'll have r squared sinh phi 1 over phi 1 times 1 over tang phi 1 minus 1 over phi 1. Then we can cancel out some terms. Okay, and I can write this as 4 pi. So I have r here and r squared there. So I'll have r cubed. So rho C S A K CAS over phi 1 1 over tang phi 1 minus 1 over phi 1. So now that we have an expression for the total rate, we can derive our effectiveness factor. But you will see later that it is convenient to do this if our rate expression is in terms of per surface area basis. Okay? Can you remember the units of the total rate? So we defined total rates this way. So we had our per volume rate times the volume of the control volume. So the units of the total rate is, so its unit is mole per second. Okay, so that is mole per second. So first, let's define the mass of a single catalyst pellet. Okay, so what is the mass of one catalyst pellet? Okay, so we can define this as the density of the catalyst pellet times the volume. Okay, so the volume is the volume of the sphere. Okay, so 4/3 pi r cubed. Okay, so therefore, the rate in per kilogram basis, okay, so in our notation, that's negative RA with single prime. Okay, so that's equal to the total rates divided by the mass of a single catalyst pellet. So we'll have 4 pi r cubed rho C S A K CAS over phi 1. Okay, divided by this. So I'll just multiply it by the reciprocal of this. So 3. So I'll have rho C here, and then 4 pi r cubed. And then we have our terms inside the bracket. Okay, so density will cancel out. So 4 will disappear, and so is pi and the r cubed. Okay, so we will have 3 SA K CAS all over pi 1 times 1 over tang phi 1 minus 1 over pi 1. Okay, so from here, we can derive the rate expression in per surface area basis. Okay, so in our notation, that's negative RA double prime. Okay, so what do we do with this? So the units of this is mole per second per kilogram. And we can use the SA. So what do we do? Do we divide this or multiply this by SA? Okay, so we can divide this by SA to get per meter squared basis. Okay, so this is equal to RA prime divided by specific surface area. Okay, but looking here, you will see that we have one SA here, so that will just cancel out with this one. So this one will be 3 K CAS over phi 1 times 1 over tang phi 1 minus 1 over phi 1. Okay, so now I have this. So this is my actual observed rate, okay, in per unit area basis. So now let's define this rate in the absence of internal diffusion resistance. Okay, so RA double prime. Okay, so no resistance due to internal diffusion. Okay, so again, this is as if the concentration everywhere in your pellets, is at all points inside the pellet, is at the surface concentration, okay, at CAS. So this is simply K times the surface concentration CAS. Okay, so now our effectiveness factor, eta, is equal to the actual observed rate, RA double prime, divided by the rate in the absence of the internal diffusion resistance. Okay, so this is equal to, okay, so this divided by this. So this term here will just cancel out with this. So my effectiveness factor is, okay, so 3 over phi 1 times 1 over tang phi 1 minus 1 over phi 1. Okay, so we have derived the effectiveness factor for a first order reaction. This is the expression that we just derived for the effectiveness factor. We can plot the effectiveness factor as a function of the Thiele modulus phi 1, which shows that for small Thiele modulus, the effectiveness factor eta is nearly 1, so no diffusion resistance. And for large Thiele modulus, the effectiveness factor eta becomes small. You can also see on this plot that at large values of Thiele modulus, the effectiveness factor starts to behave like 1 over phi 1. Okay, the inverse of the Thiele modulus. This is because as phi 1 gets large, 1 over tang phi 1 goes to 1. And this dominates the 1 over phi 1 inside the bracket. The bracket then just tends towards 1 and eta behaves as 3 over phi 1. So to recap, small values of the Thiele modulus phi 1 means that the effectiveness factor eta goes to 1 and the internal diffusion resistance is negligible. For large values of the Thiele modulus phi 1, the effectiveness factor eta gets small, like 1 over phi 1, and this means that the internal diffusion resistance is very large. The effectiveness factor eta is the actual rate divided by the rate in the absence of internal diffusion resistance. Now, since the effectiveness factor eta measures how effectively the catalyst is being used, we can use it to calculate the actual reaction rate from the surface rate. So instead of solving the second order differential equation to get the concentration profile and then integrating to get the total rate, we can calculate the Thiele modulus, which is for a first order reaction is very simple. So the Thiele modulus for a first order reaction is simply the square root of K times R squared divided by the diffusivity coefficient. And we can use this to get eta from our formula. Then we just have to calculate the reaction rate at the surface concentration, which you should know from topic 2 when you write expression using the Langmuir-Hinshelwood or the Ellie-Rideal mechanism. So the rates that we derived from topic 2 are the rates at the surface. So we can just multiply them by eta, the effectiveness factor, and we get our actual reaction rate. So we don't have to solve the second order differential equation and perform integration by parts. So here we have negative RA prime. So this is our actual reaction rate. So we can express this as the actual rate divided by the rate at CAS, the surface concentration, times the rate at CAS. So this bit is just eta, the effectiveness factor. So negative RA prime is simply equal to eta. Again, we can calculate this from the Thiele modulus. And the Thiele modulus for a first order reaction is very simple. So times the reaction rate at CAS. Okay, so this is negative RAS prime. So this is the surface reaction rates, the rates that we have been writing in topic 2 for Langmuir-Hinshelwood or the Ellie-Rideal mechanism. Note that negative RA prime is defined as the reaction rate per unit mass of catalyst. So we can multiply by the catalyst density to get the reaction rate per unit volume, negative RA. So lastly, as the effectiveness factor is a function of the Thiele modulus, and the Thiele modulus is a function of the catalyst particle radius, you can see that the overall reaction rate will also be a function of the pellet radius. So now, using what we have covered so far, try to answer the following question. If we have an exothermic catalytic reaction, A goes to B, that is internal mass transfer limited, which of the following options would definitely increase the rate of reaction? So A, increase the reactor temperature. B, choose a catalyst with a lower porosity. C, use a smaller catalyst pellet. Or D, increase the pressure. Pause the video now and think about each of these options and how they affect the rate of reaction. So, looking at each option in order, so for A, if we increase the reactor temperature, we will increase the rate of the surface reaction, but it will not make a difference to the overall rate because it is the diffusion that's controlling it. So for B, if we have a catalyst with a lower porosity, then there are fewer pores and a lower surface area for the reaction. The effective diffusivity is also proportional to the porosity, so that will decrease too. So we will make things worse. Option C, if we use a smaller catalyst pellet, what would the effect be? To understand this, we need to understand how the Thiele modulus and effectiveness factor depend on R. Recalling that phi squared is equal to R squared times K times SA times rho C times CAS times N minus 1 divided by DE, we can see that reducing the catalyst pellet size reduces the Thiele modulus. If we remember how the effectiveness factor eta changes with the Thiele modulus phi, then we can see that we want a small Thiele modulus phi to get the effectiveness factor eta close to 1. Whereas a large Thiele modulus phi makes the effectiveness factor eta go to 0, like 1 over phi. So we want the Thiele modulus phi to be small, and therefore reducing the catalyst size will increase the effectiveness factor and therefore the reaction rate. So option D, increasing the pressure will drive the adsorption of A onto the solid surface more to the right of the reaction, towards more adsorbed species. Recall also the shape of the reaction rate versus partial pressure curves we saw in topic 2 lecture. However, as with increasing the temperature, this only affects the surface rate, and the overall rate is controlled by the internal diffusion. So increasing the pressure will not increase the overall reaction rate. We have used the Thiele modulus and the effectiveness factor to describe the relative rates of reaction and diffusion in catalyst pellets. There is another similar criterion that can be used to do the same thing. This is called the Visepreter Criterion, which is defined as the effectiveness factor eta times the square of the Thiele modulus, so phi 1 square. Since eta is the observed reaction rate divided by the surface reaction rate, and phi 1 square is the surface reaction rate divided by the maximum diffusion rate, the Visepreter criterion therefore represents the overall reaction rate divided by the maximum diffusion rate. Multiplying through the expressions for eta and phi squared, we get that CWP, which is the Visepreter index, is equal to this expression. So try deriving this for yourselves, remembering the definition for the Thiele modulus for a first-order reaction and the relationships between the different rate variables. So the volumetric rate, the rate per mass of catalyst, and the rate per surface area of the catalyst. So if the Visepreter criterion is much smaller than 1, then there will be no diffusion limitation. The surface reaction rate will be the controlling step. Conversely, if the Visepreter criterion is much larger than 1, there will be an internal diffusion limitation. So far, we have considered only spherical particles and first-order reactions. The Thiele modulus can also be approximated for a number of different shapes as follows. N is the order of reaction, and L is a length parameter that takes on different values for different shapes. The relationship between the effectiveness factor eta and the Thiele modulus phi can also be plotted for different shapes and reaction orders. On the left, you can see that the curves are very similar for different pellet shapes. So we can use the same formula for any shape with only a modest error of at most 16%. The same is true for different reaction orders, as shown in the graph on the right. And here you can see an example of a plot of the effectiveness factor versus the Thiele modulus using experimental data for a Fischer-Tropsch process. So here you can see that the behavior of the experimental data follows closely what we discussed about the effectiveness factor and the Thiele modulus. Fischer-Tropsch process is becoming an important process for the future because it can provide an alternative to using fossil fuels to provide chemicals and transport fuels. Research has been underway to develop processes that can produce syngas, which is a mixture of hydrogen and hydrocarbon, from renewable sources such as biomass. This syngas can then be used in the FT process, in the Fischer-Tropsch process, to produce long-chain hydrocarbons that we need for the chemical industry and for transport fuels. So now you know how to analyze a Fischer-Tropsch reaction if ever you encounter it in the future as a practicing chemical engineer. The last thing we need to talk about is the effect of the heat of reaction. So far, we have assumed isothermal conditions within the catalyst pellet. That is, we did not consider the heat of reaction. Now, the curves for the effectiveness factor, eta, versus the Thiele modulus, phi, can be extended to account for non-isothermal conditions, as shown in this graph here. First, the activation energy and the heat of reaction are expressed in dimensionless form on the right here. Then you make a graph for a given dimensionless activation energy. Here it is 20. And you plot several curves for the effectiveness factor eta versus the Thiele modulus phi, each one for a different value of beta, the dimensionless heat of reaction. Beta equal to 0 is shown roughly in the middle, and this is the curve we have seen before. The effectiveness factor decreases for decreasing beta. When beta is less than 0, this corresponds to an endothermic reaction. So the temperature goes down inside the pellet and the reaction rate slows down. The curves above beta equal to 0 are for exothermic reactions with beta greater than 0. In these cases, the temperature inside the pellet increases, speeding up the reaction. What can happen is that although the concentration goes down due to the diffusion limitation, the rate can still increase due to the higher temperature. Overall, the reaction rate inside the pellet can be higher than the surface reaction due to the higher temperature, and so the effectiveness factor can be greater than 1. Much greater than 1 in some cases, as you can see. Some of you may have noticed that the curves with large beta, the highly exothermic ones, have a funny shape. If we specify a particular value for the Thiele modulus phi, then we can find 3 different values of the effectiveness factor. What this means is that we can find 3 different steady states depending on how the reactor is started up. Looking at the 3 cases, A, B, and C in turn, A is called an extinguished steady state. The reactant diffuses into the pellet, but not much reaction takes place. The temperature does not increase much at all. B is called an unstable intermediate steady state. Its behavior is some way between A and C, but it's hard to keep the reactor at this state. It wants to go to either A or C. C is called the ignited steady state. Here, the temperature is much higher inside the pellet, and the reaction rate is much faster too, depleting the reactant quickly. So the concentration goes down to nearly zero inside the pellet. The effectiveness factor is very high due to the higher temperature and reaction rate inside the pellet, much higher than at the surface concentration and temperature. To summarize this lecture, first, we derived a material balance equation for the reaction and diffusion in a spherical particle so that we could obtain the concentration profile inside the pellet. When we did this, we converted the differential equation to dimensionless form and found that all of the constants can be combined to form what is known as the Thiele modulus. The square of the modulus is the rate of surface reaction divided by the maximum rate of diffusion inside the pellet. The general form of the Thiele modulus is given here, and for a first-order reaction, it is simply the catalyst radius multiplied by the square roots of the surface reaction rate constant K divided by the effective diffusivity dE. The value of the Thiele modulus indicates whether the catalytic reaction is a surface reaction limited, so for small Thiele modulus, or diffusion limited, when the value of the Thiele modulus is large. The effectiveness factor eta is defined as the observed reaction rate divided by the rate at the surface concentration. That is, if there were no diffusion limitation. For a spherical particle with a first-order reaction, we showed that the effectiveness factor depends on the Thiele modulus in this way. If you calculate the Thiele modulus, then you can get the effectiveness factor from this expression and therefore calculate the overall rate of reaction from the reaction rate at the surface concentration. The overall rate is the surface rate multiplied by the effectiveness factor. Lastly, we looked at another method for analyzing the overall catalytic reaction process. The Visepreter Criterion is defined as the observed reaction rate divided by the maximum diffusion rates. It has a simple form in terms of the Thiele modulus and the effectiveness factor. It is phi squared times eta. When the Visepreter criterion is much less than 1, then this indicates that there is little or no internal diffusion resistance. When it is much larger than 1, this means that the surface reaction is faster than the internal diffusion, and so the internal diffusion is the rate limiting step.